Alright, there we go. What's up, guys? Here we are with another streaming talking about Vulkan, and this time I want to cover something more exciting than just filling structures, which is going to be part of the stream anyway. And I want to make this triangle a little bit more interesting. So let's see what is the current situation. We've got our back buffer blit with some nice Vulkan image, and then on top of it we drew a triangle, a red triangle, right? So what do we do now? We are going to push some data into the shader, and let's say we want to make it spinning, which is a nice thing to do. As always, the next stage of the triangle is a spinning triangle, right? With a changing color maybe as well. So let's dive into that. In the meantime, I have discovered that my image is no longer available. Dude, here it is. Here I am back again. Not that is very interesting anyway, so. Oh, by the way, I haven't changed the title of the stream. And this is going to be uniforms. Good. Everything consistent now. So, where do we start with? Let's get back to our image here and start to work out from here. So we've got our pipeline, our shader, and we have to change the layout of our pipeline because it will get some new data into it. After we've done that, we are going to change the command buffer as well in order to set the descriptor set, and then we are also going to create a descriptor set layout, and here we don't see it, but there are memories, so other objects that will get piped into well, not piped but referenced into these objects. So let's start with something, and we are going to begin with the pipeline. So dear Vulkan, please pop up on the right side of the screen. Here you go. And from here, let's start with a pipeline. So let's go to the description stuff. Let's see, vertex input, that's still nothing, and we go down straight to layout, which references our layout object, which is here. And yes, we have 0 layouts, which means that we have to populate this structure in order to make sense of it. So again, we go one by one these structures and start with, as usual, we start with an array. So we forgot, what's it say? Set layouts. So let's say the pset layouts is going to be something, right? That's an info layout sets. And we can even say that this is going to be an array. So stud array of vk descriptor set layout, and we're going to create one of them. Why an array? Because this will probably grow super easy and we want to make it as an array anyway. So that's it. Let's populate, shall we? Cool. What's in descriptor set layout? Not the hub that I expected. So there's pretty much nothing, is it? Descriptor set layout is probably an object. Yeah, this is an object. So it needs to be properly created as an object. So device create descriptor set layout unique, and it will need a create info descriptor pipeline descriptor set. How do I call it? Descriptor set layout. Descriptor layout. Let's say descriptor layout, or descriptor set layout, or dset. Oh well, anyway, info. Okay, then vk descriptor set layout create info, and there it is. Or let's just remove the pipeline from the name, and this is going to be a vk descriptor set layout. So what's in the info? What's in the info? We've got binding count and bindings. How many of them do I even need? Descriptor, so binding count and the bindings. Okay. So binding count let's see if there is any help from the constructor. Binding count, let's say it's just 1. And then bindings. So what is in bindings? The binding, the descriptor type. Okay, there's quite some data. So I'm wondering if we just need one descriptor set layout. So it's a set of descriptors, I guess, but we only need one, don't we? So let's say we only need one then, and that is going to be this guy here. I don't know where to use many of them and how to use. It looks like one should be enough. And get okay, that's it, right? Then we start an array. Now I guess we are good with an array. VK descriptor set layout binding, and one of them. So descriptor set layout bindings. Get that, dude. And you are good with this. Awesome. Does that? Unique. A unique guy here. And everything now is good to go. We've got this guy here. Then we've got these layout binding, and it starts to fill in some of these structures. Or why not just doing it in a flat fashion way? So descriptor type, descriptor count, shader stage flag, mutable. Not really. I mean, there's not much going on there. So I guess we can just quickly run constructors. So at binding 0 we have a VK descriptor type which is going to be a uniform buffer. Descriptor count. What is descriptor count? Descriptor type, descriptor count. What the hell is that? And this is the type of questions that bring me to the documentation. Let's see what is in the manual page. So we've got the binding number of this entry and correspond to a resource of the same binding number in the shader stage. Type, right. Descriptor count is the number of descriptors contained in the binding accessed in a shader as an array. Okay, so if it is an array, that is the number of things. Except descriptor type is inline uniform block, which is the size in bytes of the inline uniform block. Oh, if descriptor count is 0, it is reserved to resource that must not be accessed via any stage. Okay, so that can be skipped. So what is this? In case the descriptor contained in the binding is a number of descriptors. Oh, well, whatever. And no, 0. Descriptor type is not 0. Safe flag must be a valid combination. Okay. So definitely not the size in bytes. It's not inline. So I guess it's just 1. Descriptor count is 1. Shader stage flag. This will happen in the fragment. Immutable samplers. We don't have any sampler, and that's it. And that's all we've got, unless we already want to do the same. So on 1, wait, this is in the vertex, so this guy too. This guy will get to the vertex and it will contain a matrix, and this guy here is for the color. So we have a descriptor set. Now what? Now, okay, we've got our bindings. And we need a descriptor pool at this point. Which will get generated here. So we've got the command pool, and we also need a static vk unique descriptor pool. Descriptor pool. Okay, and that is static too. Good. Descriptor pool is device create descriptor pool unique descriptor pool create info. Let's see if it is inlineable, and it kind of is. So flex as usual, max sets. How many sets do we need? 2, I guess. Pool size count. I don't know what these numbers are for. The maximum number of descriptor sets that can be allocated from the pool is the number of elements in pool sizes. What? What? So first, what is a pool size, type, and count? It needs types and counts. Okay. If multiple size structures appear, is it even mandatory? Must have a valid pointer to an array and must be greater than 0. Okay, so that is definitely mandatory. So we can save space on this here, but we need an array of sizes. Descriptor pool sizes, which is vk. It's not a vk, it's a stored array of vk descriptor pool descriptor pool size, and we're gonna have 1 for now because we are only using one type. And as we already say, this is going to be a type. So vk descriptor type uniform buffer, and we're gonna need 2 of them. That's it, right? What's wrong? What's wrong? Too many? How? there's a type and there is a descriptor count, which is a uint. Okay, we probably need to specify that explicitly, which is dumb. It is super dumb. Yeah. Let's see if it works this way. Well, it's not. Yeah, let's see if I force it this way. Not really. An array. Whatever. Okay. We are getting through it. One line at a time. So the max number of sets, maximum number of descriptor sets that can be allocated from the pool. A descriptor set. So we definitely need what? A descriptor set for what? Well, maybe just one is enough for now, because we only want one of them. And the counts, the sizes dot size, and the sizes dot data. All right. So that defines our descriptor pool. Now, that we have a pool, let's see if we can still compile thing, and we keep having these errors. Okay, so everything compiles. Which is good, and global, what the hell, global. So everything compiles. We have our descriptor pool from which we are going to create descriptor sets. And where do we want to do that? So after we have created the pipeline layout, we could create the descriptor sets, right? We have the layout and we're going to create descriptor sets, just one for now, and that will happen from descriptor pool. No, that does not work, so it might be device. Allocate descriptor sets, and we have a descriptor set things, an info that contains layouts. So descriptor pool, easy. Descriptor pool account and descriptor set layouts, and the layout of each of them, which is just going to be one. We have the layout, right? Descriptor set layout, so that's it. And descriptor layout get, so that is the layout. And this is descriptor sets. Which is a vector, stood vector of vk unique descriptor set. So this is the actual descriptor set. That we're gonna use in different ways. All right, we have that, and I would take some time to go to the Vulkan tutorial and uniform buffers. So we have a quick look. Our transformation is in a single uniform buffer object, so we are using descriptor count1 and command call. Let's see who is. All right, so what was I doing? What was I doing? Hard to say. So we have that, and so there's definitely something to do before doing this. Let's see. We have that. Layout create. We've done this. We have gone, but we haven't defined any buffer yet. And that is what we still need to do. Acquire. Okay. Here's the updating uniform. So probably have to go to the next slide. Yeah. Descriptor type, okay. Pool size. Max sets. Create it. Descriptor set allocation. Descriptor buffer info. Okay, what? Wait. What is going on here? So descriptor set allocate, right? Allocate descriptor sets. We have done that. Descriptor buffer info. Destination descriptor. Okay, this is something new. The descriptor right. So VK update descriptor sets. That is something that we still need to do. VK update. So device update descriptor set. Okay, so what is going on is that we have created the descriptor set and we need to update it. Device update descriptor sets with template. Descriptor update template. So update descriptor sets. We need to put some data into it. Write descriptor set. So that's an array. Copy descriptor set. Probably not gonna need that. And write descriptor set. So we have an array of write descriptor set. So what is that? First of all, what is write descriptor set? Okay, destination, binding, elements, cool. It's an array. Stud array. VK write descriptor set, and we're gonna need two of them. Descriptor sets right. vk write descriptor set, and the destination will be descriptor set 0. Which will have a binding 0 and destination array element of 0, descriptor count 1, and this is probably still for the array thing or not. Or maybe this is kind of an offset. So descriptor type again, vk descriptor type uniform, and then descriptor image not, it's a buffer, yes, so we're gonna place it here, and it's not a texel buffer, so this is it, and same apply with the other uniform buffer. Descriptor buffer info is the description of the buffer. Pretty simple, huh? Is it still running? Yes, it is. Damn it. I hate allergy. So unique descriptor sets, write descriptor set, and we need a descriptor buffer info. Again, this is an array of vk and we need 2 of them. Please help. Buffer, offset, and range. So we need a buffer. So it's time to create a buffer. Like a proper buffer inline. This is getting bigger and bigger. We are 1,000 lines. We are almost an hour in. And before keep going, I'm gonna take 5-minute break. So I'll be back soon. Okay, so We are going to create some buffers, right? So we are going to create one single buffer, I would say, for both of them, since we share the same type. That seems the best way to go. So device, create buffer unique, and this will have uniform buffer info, which we will define just here. Buffer create info, and that is going to be this structure. I guess it's not a complex structure. And we probably could have just inlined it. So it only has a few flags that we don't care about right now, and we will probably never, because they seems like very advanced stuff. What about the size? And by the way, this seems like a pretty good time to introduce GLM. Which hasn't been defined yet, but I'm sure I have included it. GLM, yes, it's been already included, so I guess include GLM common, just GLM, and we will expand to it later. So we need GLM mat4, which is going to be our MVP, and GLM vec4, which is going to be our uniform color. Uniform MVP and uniform color. So the size of it, uniform buffer info dot size, will be the size of uniform MVP. Well, actually, I'm not sure whether I want to keep them in the same buffer, or why not? We can fix that later. And the size of color. Okay, so that's the size that we need. Just for completeness, let's go to the documentation. And here is the size in bytes. Next is usage, which is VK buffer usage, and it's a uniform buffer. We can leave everything as they are. So that's it. We have a uniform buffer. Then we need device allocate memory. VK memory allocate info. Size and index. So uint 32 uniform memory index is going to be find memory. We need memory requirements first, right? Device or physical device dot require memory get memory, probably not really. Device buffer memory requirements for the uniform buffer. VK unique buffer uniform buffer, store that in the variable and then dereference it. Uniform buffer. What's next? Oh, that's it. So it's just that. So uniform VK require buffer memory requirements. Uniform memory requirements is that thing. So uniform memory requirements and memory flags. So at this point we have two things to do. We can create a memory that is host accessible and that will slow down the rendering, or we can create a staging buffer from which we will access from host and then copy with a command to a device memory location, and we will be using the first method for simplicity. So vk memory property flag bits host visible and vk memory flag bits not allocate memory properties is host coherent, so that way we don't need to worry about being updated. Now, memory allocate info, device size, so that is going to be device size which is stored in uniform memory requirements dot size and the memory index. That's it. All we are left to do is to bind the buffer to the memory, which will do quickly uniform buffer, and again we haven't stored the return value anywhere, so vk unique device memory, which is uniform memory, and we will bind them together at offset 0. And that's it. We have our beloved buffer with no data at this time. So what we are going to do next is device map memory and even better, we will structure everything into a uniform buffers type. So that's it. And we can condense everything there. Uniform buffers, uniform buffers. Or just uniforms. So map that memory, which is uniform memory at 0 offset and vk hold size with no flags. Oh, do we need any flag? Let's see. Memory mapping flag, which is empty, so no flag required. Which means that this is a pointer to uniforms pointer is equal to stood reinterpret cast to this thing and make it an if. And at the end unmap it. That's it. After doing it, then we will just copy our uniforms to it, and that's it. Uniforms. Uniforms dot color is going to be glm vec4 of 0 1 0 1, and the uniform dot mvp is going to be glm identity glm mat4, which should give us an identity, but just to make sure, let's include glm gtc metric transforms identity of a glm mat4. Okay, we've got everything in place for the buffer point of view, and we get back to our descriptor set. So we need to provide the buffer, which is uniform buffer at a device offset. Which is offset off. The structure is uniform buffer T MVP, which is 0, and the range is size of uniform property MVP. What? Okay. So that's it, right? That range. Let's make sure that we are getting the right data. It's the size in byte that is easy to use for this descriptor update, or whole size to use the range from offset to the end. Not really. Not what we need. Then MVP and call. And call. Okay, now back to our descriptor set. We need to specify all the things and the buffer. The buffer, descriptor buffer info. It is going to be that and that. Are you cool with it now? You've got all you needed. Okay, this is missing. Here we go. So this will probably not get a unique, so we have to dereference it. Yes. We have the descriptor set, and now let's plumb it into the function. There you go. Null, pointer here, and that's it. You've got what you wanted. So we have allocated the descriptor set. We have described the buffers for each of them, and then we have wrote the descriptor set. Is there anything else we need to do? Bind the descriptor set at this point. Otherwise it will not get through. Bind descriptor set. So vk pipeline bind point graphics, the layout pipeline layout. Why does this keep asking for the layout? The first set is 0. The descriptor sets set. So where is the descriptor set? unique descriptor set, so that is it. Dynamic offsets. So descriptor sets, descriptor sets. Is this was this an array? Yes, it was an array. So the 0, 1, and reference it, but get the underlying Vulkan type, and then we have no dynamic offsets. That's it. Are we good with it? Unique descriptor set. Okay, something is still wrong. Probably don't need that. Cool. Bind them. Compile it. So we have gone through different stages before coming to this point. And let's see if we get any complaints from... Yes, we do have many complaints. Map failed. Why? Update descriptor sets must be a multiple of device limits. Ouch. Of 100, which is to 56. Which is 20. Matrix is 9 by 4, which is 32. No, it's not 9, it's 16. 16 by 4, it's 64. Ouch. And also, why are we getting a memory map failed? Where that map is coming from? Maybe it's not. Yeah, it's not memory map, it's device lost. Okay, it's lost device. So stop it. We have a problem here. Offset 40 must be a multiple descriptor 1 offset. So let's see. Descriptor 1. So this is the buffer, descriptor buffer info. buffer info.offset, which is this one, which is 40. Which is 40. Yes, so 40, which is 64, and it needs to be 100. So C++ struct alignment align back. Yeah, align off and aligned. So what? That's not very helpful. Let's see. Let's see how this works out. All right. And that is still not doing what I expected. So let's try again. Shit. So it looks like I have to do that manually. Really? Come on. So a pad. So we've got 40 and we need to go up to 100, which means we have 60 to go. Okay. Which is a waste of space, isn't it? Uh, 160. Give me hacks, please. Offset A0 and range. So what is the offset? What is A0? The offset of color weird. What the hell? Let's say we've got one of them. Which brings us to 44. From 40 to 44. What the hell? Why not 41? Two. Oh yeah, because that is already aligned to 4, so this shouldn't change much. Still 44. We are at 80. and 2 more, 20 more. Oh, which is about right, or not? Yes, so yeah, my bad. So it's like 100 minus size of MVP, let's say that. So it's now 100. Cool. And that's it. We get no errors. Right, so this kindly says to us that we need to provide a padding. I mean, buffers need to be aligned at 100 hex bytes. So that's it. That's what we've done. Alignment. Okay. So everything is now in place except for the actual shader that it's not using the data yet. So layout, binding is equal to 0, uniform uniform, we need a uniform block like this. And yes, so uniform can I just leave it unnamed? Mat for MVP, and that's it. Let's call it UBO. Will this work? Unexpected. So it needs a name, UBO type. Yeah, that works. And here we will UBO.MVP multiply and that's it. How about we don't use it? No, we are going to use it. So layout, binding to 1 is a uniform UBO type of vec for color UBO, and that will be plugged into ubo.color. Compile, works, run, enjoy. Come on. Yes, 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 yes. It's green as expected. It is working like butter. Awesome. Super awesome. So let's make this rotate a little bit. So instead of an identity, we are going to require some GLM magic, GLM GTC or GTX, Euler angles. So GLM mat for Euler Z, rotate around Z, GLM radians of 45 floating points. 45 degrees. Let's see if our triangle rotates, and yeah, it kind of does it, but it's weird. It is super weird. What is going on? It's definitely weird. So at this point, I would suggest to grab these and move them into the rendering loop. Submit the rendering. So instead of rendering all the commands, we are going to render the back buffer, so only one. Submit commands and point it and point that to the current index, which is back buffer value submit fence so instead of using a fence, back buffer semaphore, see, submit info dot wait semaphores. So we need to wait for this semaphore. Okay. And we will signal a semaphore ourselves. So we're not going to use any fans. VK unique semaphore render sem, which is device create semaphore. We need to synchronize everything at this stage instead of just waiting for the queue to complete. Okay, there are no flags, so that's just it. Create the semaphore. Unique. Create that damn semaphore. Okay, forgot it. Then we just pass it to render semaphore.get. So this is the one that you need to signal, which is the one that the presenter must wait to. And that's it, right? Nope. So queue forward progress. Nothing's working. Draw state, the command buffer, but it has submitted many times. You are right, my friend. I am so sorry. So I said this was going to be a one-time submit, but then I've used it many times. So we will remove that option. And then we get into some other trouble. Begin command buffer require parameter no. What? So it must be... Dude, what do you expect? What? So begin info. It's got a usage. Okay. You happy right now? Okay. So that has no way to be signaled. Okay. Why is that? Q4, so is waiting for a semaphore that has no way of being signaled. Why is that? Mate, render, semaphore, signal semaphores, wait semaphores, back buffer, which is being used here. So that comes from the queue. And why is that? Okay. Time to go to the documentation and a semaphore to signal. It definitely says that. Type binary. Which is semaphore type? So it doesn't want to wait for that. Has no way to be signaled. Who is waiting for that? I see. Wait a second. Maybe I need to. Yeah, count. So this is one. Man, submit info dot wait. Count is 1. So that was the problem. Pointer is not enough. You need to provide the count, obviously. So what now? What do you want from my life? Wait, destination stage mask, right. You need to provide a destination mask for each wait. Submit info dot wait destination mask. And that is the output. Pipeline stage flags. Stir array vk pipeline stage flags of 1, and that is wait stages, which is vk pipeline state flags flag bits output. And that is wait stages dot data cool and we are good to go. We just cleared everything. We are rendering at every frame, and now we want to update the memory. Get that bad boy memory updated, and we want to access them directly. So MVP is going to be, give me a static float angle starting at 0, and then angle increments by GLM radians of 5 degrees, and the MVP will be our angle Z of that angle. So that's it, and it rotates in a very weird way. It is super weird. Yep, that is because the aspect ratio is not ideal. So how do we fix that? We are going to introduce GLM ortho where float aspect is going to be surface caps dot current extent dot width and surface caps dot current extent dot height. Floating, obviously. Float. All right. So what happens is that we keep Patatino. Patatino. bottom is minus aspect, and that's it. Let's see if this change fixes the aspect ratio at least. And it definitely worsens it. So it might be the reverse. Yes, it is. However, it is not centered. It's not in the center. And why is that? Well, anyway, no problem with that whatsoever. The important thing is that we've got our rotating triangle with maybe a changing color as well. Dot red G, and I'm seeing of that angle. Okay, let's boost it a little bit. Are you sure? Yeah, it's just seen. Oh, scusa, piccolino. Trattellino. Okay. Color changes super rapidly. Maybe too fast. Okay. There we go. Color changes, triangle rotates, everything is working smoothly. We don't have any warning. We don't have any message from validation layers. We don't have any warning while compiling. Super duper clean. And that completes our journey for the uniform buffers. So I would set that to done. So I can stop this and go to make some lunch. Bye.